Okay, hello everyone. Good morning, all of you.
Good morning, sir.
Good morning. So we start with a quote today, and today's quote is: "The price of success is hard work. Not only hard work, dedication to the job, and the determination that whether we win or lose, we have applied the best of ourselves to the task at hand." Okay, these are the main three things we need. Hard work is needed, and the dedication to it is needed. Okay, means passion, and the other thing is we should have the determination whether we win or lose, we will put our maximum effort, right? So that is the best of ourselves. That is main important. So this is actually from Gita, we say Kama Siddhanta. Okay? We have to put all the effort. Don't think about winning or losing. But when you put the effort, automatically winning will be there. But our focus should not be on winning. But our focus should be to put the best. Yes, to put our best of ourselves. Okay, so that is one of the main thing that we have to remember. And today is the birthday of the great Homi Baba. I think everybody is familiar about him. He is our father of Indian nuclear program. And Homi Baba was an Indian nuclear physicist, founding director, and professor of physics at the Tata Institute of Fundamental Research (TIFR). And colloquially is known as father of Indian nuclear program. Baba was also founding director of the Atomic Energy Establishment Trombay, AEET, which is now named as BARC, Baba Atomic Research Center, in his honor. And TIFR and AEET were the cornerstone of Indian development of nuclear weapons, which Baba also supervised as director. And Baba was awarded the Adams Prize and Padma Bhushan, and he was nominated for the Nobel Prize for Physics in 1951 and 1953 to 1956. So he continuously was nominated for Nobel Prize. But okay, anyhow, there will be some politics also. Getting so many prizes, though worth is there, they cannot give to the same country like India. Okay, and today we will have the what is called as unstructured grid generation. Okay, last class we have completed the structured grid generation, where we have discussed about algebraic grid generation and then PDE grid generation. So in the PDE grid generation, we have discussed about elliptic grid generation, hyperbolic and parabolic grid generation. So in the elliptic grid generation, mainly it is confined to closed domains, and also we get orthogonal grid. That is one of the main important with that. One is the orthogonal grid, and another second one main important thing is any discontinuities in the domain gets smoothened out because of the second order derivatives present in the equation. So we have seen how to use it. So we have to solve the elliptic equations, mainly given elliptic equations in the physical domain, and which cannot be solved there. So we have to transform into the computational domain, that is the eta coordinates, and we have to solve them so that we will get the orthogonal grid. And then we have discussed about the hyperbolic grid generation. In the hyperbolic grid generation, it is mainly can be used for open domains, which cannot be used by elliptic generation. And another thing is it uses matching method to solve it, which is very, very fast. So to get the equations in the hyperbolic grid generation, we take two constraints. One is orthogonality constraint, another is geometric constraint. And in the geometric constraints, again, there are two methods. One is Salaria approach, and another is arc length approach. So once we get two equations from these two constraints, we have to solve them. And they are nonlinear equations. So we have to linearize them using Newton's method. So once you linearize them, then you have to solve it using matching method. And meanwhile, we have proved that there are hyperbolic equations in the process. Okay, so that is the thing. And then we talked about parabolic grid generation, which will have the facility of, because hyperbolic grid generation will not smoothen the discontinuities. Okay, that is the disadvantage with hyperbolic. So if you can have a parabolic grid generation, right, which can be solved using matching method, and also it smoothens out the discontinuities because of the second order derivative present there. So that is the advantage of that. Okay, so these are the things we have discussed. Okay, now we will concentrate on unstructured grid generation. Is everything okay?
Yes, sir.
Okay, because I don't know whether suddenly audio stopped or video stopped. I will not know unless you say yes, sir, or okay, sir. Okay, right. Today we'll have the unstructured grid generation in the class 28. Okay, this is taken from CFD volume 2, chapter 17 by Hoffman and Chiang. Okay. Okay, here the main thing between structured and unstructured grid is okay. Okay. So grid points cannot be associated with grid lines in unstructured grids. As I told, structured grid means any grid point can be identified by the grid lines. So that is the main thing. And grid points here must be individually specified. Okay. And finite volume method and finite element method are used for unstructured grids. And if we can have two-dimensional elements or three-dimensional elements based on the domain. Okay, if it is two-dimensional elements, we have two types of elements will be there: triangles and quadrilaterals. And if it is three-dimensional elements, we will have pyramids or tetrahedrals. Okay, so these are the things we will have the elements. And triangular elements are generally the most flexible shape to fit any type of boundary. Whatever be the type of boundary, we can put fit the triangle elements. But quadrilateral elements, for some of the corners and all, we cannot make quadrilateral elements there. So triangular elements are the most suitable elements for any type of flexible shape. And it can be used easily to fit irregular, simply and multiply connected domains. And it can be easily coupled with grid refining methods and adaptive grids. As I told in the last class about adaptive grids, so we can use with irregular grids or we can refine the grids while doing the calculations, which are called as adaptive grids. And but only thing is, the main complication is it is difficult to code and needs sound background in the data structures and data bookkeeping skills. That's what I was telling previously. We have to know about the links. Okay, how the each node is linked, each triangle is linked. Okay, each element is linked to the neighboring elements. Unless I know that properly, keep bookkeeping we don't do, then it's difficult. So we have to know those techniques for doing the unstructured grids. Okay, this is about unstructured grid. And so how to generate unstructured grids? There are two types steps. One is domain nodalization. I have to have some nodes, some uniformly distributed nodes I need. Okay, once I have the nodes, then I have to do the triangulation. And triangulation, again, there are two methods. One is advancing front method, and another is Delany triangulation method. So we will discuss all of them step by step. Okay, first we will see how to nodalize. So nodalization. So here we consider a irregular domain. Okay, shown in this next slide. And here we have taken a doubly connected domain. It can be multiply connected, simply connected, doubly connected, whatever it is. So for having clarity, we have taken a doubly connected domain here. And here I have an outer boundary and there is inner boundary. And so outer boundary nodes, we name them as 1, 2, 3, etc. 14, counterclockwise order. So we have to follow a particular type of notation. That is important. So we number them in counterclockwise order. Okay, this way. And inner boundary nodes, because outer boundary nodes are up to 14, so it continues with inner boundary nodes 15, 16, 17, etc. But these are put in the clockwise order. Outer boundary anti-clockwise order, inner boundary clockwise order. And we make edges. And the edge is a line segment formed by connecting two successive nodes. So these neighboring node, we connect it by segments. They are called edges. So edge is defined by two nodes ik, where I and k are the endpoints. And edge can be denoted as jik. J is the edge number, and ik are the end nodes. Okay, so this is the way we follow the notation. So you can see here all these things. So we number them 1, 2, 3, 4, 5, etc. on the outer boundary in the counterclockwise order up to 14, and from 15 onwards, here we are putting in the inner boundary 15, 16, 17, 18, 19, 20. So like this, we have to number these nodes. Okay, so after that, what we do? Domain normalization procedure. So what we do is, when you have the domain, somehow this. Okay. Okay, the minimum and maximum y locations of the domain, y min and y max, are determined. Okay, so in the domain, this is the y max line and this is the y minimum line. Okay, minimum line and maximum line we have to draw and find out what is y minimum and y maximum. And then I have to draw number of horizontal lines here. At what distance? So before, to find out that, I have to find what is called as average length of the edge. So that is done like this. Average edge length is calculated. L average is equal to sigma Lj by m. So this is length of edge j. So all the edge lengths we have to sum up, and then by the total number of edges will give me average edge length. Okay, so this average edge length I have to find out. Then I have to draw horizontal lines between y min and y max with the L average distance. Okay, like this, we number of horizontal lines I have to draw such that the distance between two successive horizontal lines is L average. Okay, like that we draw number of horizontal lines. Okay, that is the next step we do. Okay, create horizontal lines at different levels across the domain between y min and y max. And the spacing between the two successive horizontal lines can be set equal to L average. So how many lines we will get? Y min, y minus y max, or y max minus y min by L average. These are the number of horizontal lines we get. So after drawing the horizontal lines, what I have to do is I have to find out the intersecting points of those horizontal lines with the boundary. Okay, that's what I have to do. So determine the intersection points of horizontal line, say line y equal to d, and the boundaries. For this purpose, one must check to see whether intersection points exist or not. So when I consider a horizontal line, whether there are intersection points exist or not, I have to check. And how to check it? So So when I take this particular line, suppose, so I have to see the y of this line, because the whole line has only one single y. Okay, so suppose that is capital D. So this y of line D should be in between the y coordinates of the two endpoints of the edge. Then only I can say it is cutting this. So if I say this line, this edge will not be cut by this particular edge. Okay, because both y's are higher than this particular y of this horizontal line. But if I take this 8, 9 edge, so one of the y is more and one of the y is less compared to the y of the horizontal line, then I can understand that it is cutting this particular edge. Okay, that is the way I have to make a check. So this is the way I have to take check. So for an edge ik, there exists an intersection point if yi minus d into yk minus d is less than 0, where d is the y of the horizontal line that I am considering. Okay, so if it is one is that side and one is this side, so the differences, if you multiply, it will be less than 0. One will be positive, one will be negative. If this is equal to 0, means it is going through one of the edge, one of the endpoint. one of the endpoint. So yi minus d into yk minus d equal to 0, and d equal to yi or d equal to yk. So it is going through one of the end nodes. Okay, so this is the way we can find out whether it is intersecting or going through one point. And once I know it is intersecting, I have to find out the point of intersection. So the x coordinate of the intersection point is determined according to x is equal to xi plus d minus yi by xk minus xi by yk minus ya. It is nothing but y equal to y minus y1 by x minus x1 is equal to y2 minus y1 by x2 minus x1. Okay, this is the slope, y2 minus y1 by, or x2 minus x1 by y2 minus y1. This is slope. And so x minus x1 by, this is y of the line, y minus y1 is equal to x2 minus x1 by y2 minus y1. Like that, using the straight line equation, I can find out the intersecting point. So this gives me x. Y is nothing but the height of the horizontal line itself. So the y coordinate is obviously equal to d. Any doubts?
Sir?
Any doubts?
Sir, explain again x equal to xi plus d minus.
Okay, this is, here, line equation, right? X minus x1 by y minus y1 is equal to x2 minus x1 by y2 minus y1. Is it okay?
Yes,
This
yes.
line? Okay, so this is x2 minus x1 by y2 minus y1, xk minus xi, yk minus ya. Okay, and this is x minus x1 by y minus y1. So this is the point I want, xy. Okay, y is already known, that is y of the horizontal line, and x where it is cutting I have to know, right? Is this equation clear or not?
Yes, sir.
Okay, it is just like slope of x to the intersecting point and the slope of the whole line should be same, right?
Sir, from above equation, d is
I can
equal
find
to
out x coordinate of the intersecting point.
hello.
Yes.
Sir, from above equation, d is equal to
Y
y.
equal to y of the horizontal line.
Yes, sir. In place of d, I am putting yi, sir. This is become
Yes.
0.
No. See, ya and yk are the end nodes of the edge,
Okay, sir.
and xy I have to find out, and y is the y of the intersecting point is horizontal line y only.
Okay, sir.
Is it okay?
Yes, sir.
Right. Okay. So in that way, I have to find out the intersecting point. Okay, but there will be some troubles are there. What are they? There are some what are called as qualified useful lines and unqualified lines. And what do we mean by qualified lines? Lines which cut the boundaries with even number of points. Okay, if I have simply connected domain, no problem. Any line you draw, it cuts at the both endpoints only. Okay, 2 endpoints will be there. And but sometimes what happens is in the boundary, edges are there, right? So the line may go through one of the edge. The whole line, whole edge may be in the line. I will show you that. An edge is located along the horizontal line. That is line coincident with edge 7, 8. You can see that edge. Okay, here, if I draw this line, okay, this is going through like this. And how many intersecting points are there for this line going through 7, 8? 7, 8, and also this point will be there. There are 3 points will be there, right? Am I clear?
Sir?
Yes, sir.
A line going through the 7, 8 edge. Okay, this edge is horizontal. One of the edge on the boundary is horizontal. Am I clear?
Sir, what is D? Capital D.
Capital D is height of the horizontal line I am considering. Y of the horizontal line that I am considering. Okay, if this is line, if this is the line, suppose, okay, line going through 8, 9, which is intersecting 8, 9. Okay, so this is the line I am considering, and so the y of this line, horizontal line, is taken to be D, and this is xi yi and 9 xk yk. Is it clear? 8 is xi yi, 9 is xk yk, and the height of this horizontal line is y, and I have to find out the x of that point.
The height from 8 or y minimum?
Hmm?
D is the height from
Y
y, from
yeah,
y
this,
minimum.
yeah, y min is there, height from some horizontal, some x-axis, and y max also height from x-axis, and the d, capital D, is y of this horizontal line from the x-axis.
Okay,
X-axis is somewhere down, right? Is that clear?
Yes, sir.
Yeah. Okay. Now, if I take a line going through 7, 8, okay, so there will be 3 intersecting points. Similarly, if I take a line going through 19, this also will have one edge, this boundary point, and this 19 and this point. There are 3 points. Okay, these are the points which are called unqualified. And if there are only 2 or 4, if I take this particular line, okay, I have 1, 2, 3, 4 intersecting points are there. No problem. If I have odd number of intersecting points, I will have problem. Okay, what to do now? Okay, an edge is located along the horizontal line of edge 7, 8. Okay, if edge is horizontal, then it's going through that. And
Sir,
yes,
sir, from that expression x equal to
okay, right, this expression. Okay,
is it is the equation of each edges.
see, I will tell you, right? Okay, now this point is there, right? This particular intersecting point is there. For this, I need x coordinate. Okay,
Yes.
could you see my cursor?
Yes, yes, sir.
Okay, and 8 and 9, 8, 9 edge is cut by this particular line. Okay,
Okay.
and for this intersecting point, I know y coordinate because it is on the horizontal line which is cutting, but I want x coordinate. Okay,
Okay, sir.
and the slope of this line from 8 to this intersecting points, that is x minus x1 by y minus y1, and y is d. And the slope of the whole line is x8 minus x9 by y8 minus y9, or xi minus xk by yi minus yk. Okay.
Okay, sir.
So both slopes are same. That's what I am using there. X minus x1 by y minus y1 is equal to xi minus xk by yi minus yk. Okay.
Okay, sir.
Right. Like that's why that is the way I can find out. Now the next point is, if there is a line which is making 2 intersecting points or 4 intersecting points, I can find out all the 4 intersecting points or 3 intersecting points. But if there is a line going through a edge which is horizontal, okay, so then there will be problem. And if there is an edge going through one of the corner like this, so it is also having 3 intersecting points. So if there are odd number of intersecting points, they are called unqualified lines. Okay, going through 7, 8 and going through node 19. So the unqualified lines distort the uniformity of node distribution. To overcome this problem, the unqualified lines are adjusted by a fraction of L average such that even intersecting points are produced. Okay, so what we do is, okay, to this unqualified line going through 7, 8, I take another horizontal line very close to that, Okay, so I add to y coordinate some alpha L average, where alpha is very small, some 0.1 or something, so that I will get another horizontal line here. Now I will have only 2 endpoints, 2 intersecting points. Am I clear?
Yes, sir.
Similarly, for the line going through 19 also, you can just add or subtract some small fraction. So I will get another line, maybe above. If it is above, I will get 4 points. If it is somewhat below, I will get 2 points. Like that, I have to have either 2 points or 4 points, but not 3 points. Is it okay?
Yes, sir.
Now, in that way, I have to find out all the intersecting points. So then I do like this so that there will be uniform distribution of the nodes. Okay, so the order is to be arranged. Okay, once I get the intersecting points, the order is to be rearranged according to the increasing x coordinates. Okay, suppose line y equal to h. Okay, this line y equal to h, it is drawn like this. It has 4 intersecting points. Here one, here one, here one, here one, A, B, C, D. But they should be written in increasing x coordinate. So B, D, C, A, I have to write. Okay, so increasing x coordinates. Okay, in that way I have to write. And after writing that, I can divide this distance into number of nodes. Okay, so it is like this. Now interior nodes I have to get. The interior nodes are now distributed along the horizontal lines between every 2 successive intersecting points within the domain. Okay, so take each horizontal line, take here each horizontal line, and between the intersecting points, I have to divide into number of nodes. Okay, how to distribute? These are called interior nodes. Whatever I'm going to generate, they are interior nodes. And so what is the distance between the interior nodes I have to use? So that is given here. Okay, the interior nodes are now distributed along the horizontal lines between every 2 successive intersecting points within the domain. The distribution may be accomplished by a pre-selected distance, beta L average. Okay, the distance between 2 nodes must be beta L average, where beta is approximately 0.5. Okay, and the set of points P1, P2, P3, P4, P5 has been generated on that particular line. You can see here. So between B and D, there are 2 points P1, P2. Between C and D, C and A, I have P3, P4, P5. Like that, I create points interior nodes like that, so that I get uniformly distributed interior nodes also. Okay, there is one more difficulty we will face. Okay, what is that? It is possible that some of the nodes located would be too close to the boundary. Okay, sometimes the point may come very close to the boundary, but they disturb the uniformity of the distribution, and they are to be identified and removed. Okay, so an example is given. Suppose here there is a point here, suppose it comes, and if it is too close, and how to find out whether it is very close to the boundary or not. Okay, so for that, I have to do like this. So if there is a P node, okay, near to an edge ik, then if lik square is greater than lip square plus lkp square, then that is very near to the boundary or very near to the edge. So that is to be eliminated. So points which satisfies this condition are to be removed. Okay, so these are the steps we have to do. Again, I repeat, we have taken a domain here. For example, we have taken doubly connected domain, and I have to number the nodes on the outer boundary in anti-clockwise direction, and in the interior boundary in the clockwise direction. In that way, I have to number them. And after that, I have to find out what is y min and what is y max. Okay, so draw lines. And then you draw the edges connecting all 2 consecutive lines, and find out average length of the edge by finding out L average is equal to total length of all the edges by the number of edges. That gives me L average. Then between y min and y max, I have to draw number of horizontal lines with a distance of equal to L average. So the total number of horizontal lines NL is equal to y max minus y min by L average. Like that, I draw all the horizontal lines. Then each line may cut the boundary at two even intersecting points or odd intersecting points. Okay, if even intersecting points we get, it is qualified, and if it is odd, it is unqualified. Okay, if it is qualified, then I have to find out the intersecting points. So we have seen how to find out the intersecting points. Okay, so if it is unqualified, then I have to take a horizontal line which is very near to that, eliminate that, and very near to that, up or down, we have to take, so that I will get even intersecting points, and then you can find out the intersecting points. So in that way, I can find out all the nodes on the boundaries. Then I have to generate the interior nodes. And before getting the interior nodes, the intersecting points are to be arranged in ascending order of x coordinate. And each distance between two consecutive intersecting points, I have to divide them into number of nodes, interior nodes. And the distance between nodes should be equal to beta L average, where beta is approximately 0.5. Okay, so like that, I get all the nodes, interior nodes. And sometimes any interior node may be very near to a boundary edge. So if it is very near, I will get an odd shape of triangle. I have to remove it. And I have to check that if LIK square, the edge length square, is greater than LIP square plus LKP square, then I have to eliminate it. In that way, I produce all the nodes that are qualified and which are uniformly distributed on the boundary and interior of the boundary. This is called as domain nodalization. Is it clear? Is it clear?
Yes, sir.
Okay. So once we nodalize the thing, then I have to do the triangulation. Okay, there are two methods of triangulation we have seen. One is advancing front method and another is Delaney's method. Okay, so we will see one of them first. So domain triangulation, we will see first the advancing front method. Okay, here, what is a good triangle and a bad triangle, right? So in the triangulation, okay, good quality or bad quality. Suppose if I have 4 points here. Okay, these 4 points, a quadrilateral, are to be divided into 2 triangles. It can be done like this or it can be done like this. Am I clear? So which is a better one? Because I want all things somewhat uniformly, I want the triangles to be as nearly equilateral as possible. Okay, so that is called as good triangulation. If I have almost all of them very near to equilateral triangles. So that my intention is to have such type of triangulation. If it is not like that, that is called as bad quality. So I have to check that. Okay, so for this advancing front method, what are the advantages? It is simple and straightforward, and it is relatively easy to implement for numerical application. And it can triangularize concave domains without any difficulty or additional effort. Anybody knows what is the difference between concave domain and convex domain?
Sir, if we draw the line between 2 points and it lies outside the domain, then it will be concave domain, sir.
Yeah, that's right. Very good. If you take any 2 points within the domain and if you join them, it should not cut the boundary. Okay, so such is the convex domain. And concave domain, it cuts the boundary. Okay, such thing is concave. Okay, so usually convex boundaries are just like all polygons are concave, convex boundaries. Any 2 points, if you see in the domain and if you join, it will not cut it. But suppose if I take the domain which I have drawn previously, okay, this is the domain. Suppose if I take a point here and point here, and if I join like this, is it clear? It cuts the boundary. This is in the domain and this is in the domain, but when I am joining it, it is crossing the boundary. So this is concave boundary. Is it clear?
Yes, sir.
Yes, sir.
Sir,
Yes. Okay. So normally, many times concave boundaries are difficult to handle, but this particular advancing friend method can handle both concave and convex domains. Okay. So without any difficulty. And disadvantages, the scheme is not efficient as some of the other triangulation schemes. Okay, efficient means already I told. I have to get only these types of triangles, not these types. Okay, sometimes we may get poor quality. Control over grid quality is limited. Okay, so should be nearly equilateral or equiangular, good quality means. So sometimes I don't have control over that. That is the main disadvantage with the advancing friend method. But the other method, Delaunay triangulation, that is very efficient and widely used. But we cannot write our code. It is difficult. Okay, but if you want to write a code, then advancing friend method is easier to code. But you may not get good quality triangulation. Okay, so for small problems, we can do this for coding and all. Okay, how to use this advancing friend method? So first we will use it on simply connected domain, and same procedure I can use for doubly connected and multiply connected domains. Okay, now we will see the procedure. Okay, this is the domain I consider. So domain normalization I have done. So in the normalization, I got the outer nodes here and some interior nodes I got here. Okay, this is the way I got. And so what is the procedure? All the edges along the initial boundary of the domain are numbered in counterclockwise order and saved in an array E. So we have two arrays we will have. In one of the array, we will have all the edges on the boundary. Okay, all the edges along the initial boundary of the domain are numbered in counterclockwise order and saved in an array E. Okay, it is something like this. Okay, so this AB, BC, CD, DE, this is first edge, second edge, 1 AB, 2 BC, 3 CD, 4 DE, 5 EF. Like that, we store all the edges on the outer boundary. Okay, so this is one array. And how many edges are there? 12 edges are there. And the last edge is LA. Okay, so up to L are there in the outer boundary. So LA is the last edge, 12, edge 12. Okay, this is stored in the array E. And the next there are interior nodes. And that is another array I will store it. Okay, so all the interior nodes are saved in an array I. These nodes are referred to as qualified nodes. They are called as qualified nodes. And the array I includes M, N, and O. If you see in the figure, M, N, and O are stored. It can be in any order, no problem. Okay, so these are the two arrays I will have. Now, beginning with the last edge in the E array, search for the nodes which are on the left-hand side of the edge. And the search includes both interior nodes and edge nodes. And these nodes are called qualified nodes. Okay, these nodes are called qualified nodes. Out of them, select the most suitable node which has the minimum normal distance to the two edge nodes. Here the last edge is 12 LA, last edge is 12 LA. This is called as advancing friend. Okay, the last edge is called the advancing friend. Okay, so here the last edge is 12 LA. And if the most suitable node is X, okay, so suppose I found out the most suitable node is X, then what it means is LXL square plus LXA square is minimum. Okay, so the distance between from that point to the two end nodes. Okay, so this total length should be minimum. Now, three nodes LA and X, which are ordered in counterclockwise fashion, are used to form a triangle. Now that minimum distance node I have to take, and I have to make the triangle with the last edge. Okay, so that is the first triangle. In the present problem, okay, so for this LA, the nearest node is M. Okay, so LMA will become the first triangle. Okay, LMA will become the first triangle. LAM is formed. Okay, it is written as LAM in counterclockwise fashion. LAM. Okay, so this is written. Okay, but now the question is how to find out whether a given node is on the left side or right side of the edge. I have to find out first the node which is on the left side. Then I have to find out the most suitable node which is very near to that particular edge. These are the two things, right? And the first thing is how to know whether a node is on the left side or right side. How to find out. And now can you tell me for this edge LA, is it on the left side or right side? M.
Right side.
It looks to be right side, but it is not on the right side. It is on the left side. I am talking about LA. It is a vector, right? LA is like this. So you have to stand on L and face towards A. That is the way you have to stand. Now, M is on the left side or right side?
Yep, left side.
On the left side. Okay, so that is the way you have to look, not in the way I see from in the front of the figure. It is not like that. Okay, so I have to stand at L and face towards A in the direction LA, right? And then I have to see whether it is left side or on the right side. I have to see it should be on the left side. Okay, so this is the one. And how to know whether a particular point is on the left side or right side? Okay, so how to find out is this is LA vector and join L to that new node, whatever it is there, and that is a vector LM. Okay, and I have to find out the cross product of LA and LM. Okay, cross product, if it is positive, then it is on the left side. And how to know whether it is positive or not? Okay, so physically, mathematically, you can do it. Physically, this is LA and this is LM. This LA is to be rotated in counterclockwise to become LM, right? That gives me the direction of the cross product. Cross product is a vector. And what is the direction of that vector? The cross product vector is either perpendicular to the plane outside or going inside. Is it clear?
Yes, sir.
Right? So you turn LA towards LM. So it becomes counterclockwise. Means actually with the right hand rule, it is coming out of the board. And that is positive direction. So if it is in the positive direction, then it understood that that point is on the left side of the line. Okay, that is written here. You can just check. Okay, how to identify the qualified node?
So please explain again, sir. Actually, how LA is on left side, sir.
How?
LA is on left side, sir.
That's what I'm telling. You want the okay, just as I told, if you stand on L and face towards A. Am I clear? Hello?
Yes, sir.
Yes, sir.
Is it on the left side or right side now? Not A
Left
to
side,
L.
left
Okay,
side.
L to A. L to A I have to see. Okay. If
Okay.
you see A to L, then it will be on the right side.
Okay.
Okay, that is one thing. And mathematically, how to find out is find out the cross product of LA and LM. If it is positive, means it is coming out of the board. Okay. So then it is on the left side. So
Okay,
that's
sir.
the way I have to find out.
Understood, sir.
Okay. So define
Sir,
a position. Yes.
sir, what means that is most suitable node in this figure?
So that's what the point should be on the left side. So all these points are on the left side of LA, right?
Yes, sir.
And out of that, which is near to that, I have to find out.
Okay, sir.
Which is the nearest to LA. Okay.
Yes, sir. Thank you, sir.
Right. Okay, define a position vector L to A and another position vector L to M. If the cross product of the vectors is positive, then M is located on the left-hand side of the edge. Okay, then we have to find out what is the nearest, and then we can find out. So now update E. Now once I draw the triangle, so once I draw this particular triangle, okay, LMA, okay, this LMA, this line is triangle is drawn. Once this triangle is drawn, and whichever existing this edge is there in the E array, right? So this edge is to be removed from the array because this edge is already used. Am I clear? But new edges are formed. These two new edges are to be added, LM and MA. And the number is to be continued. So this previous 12 edge is removed, 11 only are there. To that, this 12 and 13 are added. Is it clear?
Yes, sir.
Yes, sir.
Okay. So E array is to be updated. And interior nodes, one interior node is already used. Now it is on the boundary. Okay. So this is to be removed from the interior nodes I. So I array and E array is to be updated after every triangle formulation. Okay. And now in the E array, what is the last one? Last one is MA. And this becomes the advancing front. Now to this, I have to find out which is on the left side and which is on the nearest, which is the nearest node. Then we can find out that B is the nearest one. Then MAB is the triangle that is formed. And then this will be removed. Okay, so like that I have to do. Just I'll show you the next one. Yeah, here. So the next triangle is formed this way. And this edge and this edge is removed, which are already there in the E, in the triangle. And this is the new edge which is formed, that becomes the last edge. And this becomes the advancing front. Now interior nodes are not updated because no other interior node is used. It's already removed. Okay. So I will be as it is, but E will be updated by removing these two. And this new one will come. Now this is 11 and this is 12. And this is the advancing front. So like that, I have to continue. Okay, that procedure is to be continued. And there is another situation comes when this edge is this particular triangle is formed. When this particular triangle is formed, all these three are removed. Okay, so this is what is called as dead end. Okay, this is explained there. Okay, steps 2 through 5 are repeated. 5 are repeated until triangle ECD is formed. This is considered as dead end because all three edges 13 EC, 1 CD, and 2 DE, which belong to E before triangulation, must be removed from the E array. And subsequently, the edge EF is now the edge 1. Now I have to renumber them. Okay, so now this will become 1, 2, 3 like that, and this comes up to here. This will become the last edge, and this edge will become the advancing front now. And in that way, I have to continue. Okay. Is now the last edge and is now continued to the triangulation. The procedure continued until all the edges in E are removed. As a consequence, the triangulation of the entire domain is completed. So like that, E and I are to be updated. I should become 0 and E should become 0. All the edges must be used so that the triangulation is completed. Okay, this is the way we have to go about it. Again, I repeat. So when we have a domain here, we have to number the edges in the counterclockwise direction. Okay, so and all the edges are added in an array E. Okay, 1, 2, 3, 4, 5, 6 like that up to 12 here. And the interior nodes will be put in another array I. Okay, so the last edge in the E array will become the advancing friend. And so to this advancing friend, I have to see what are all the nodes that are on the left side of the edge. And they are called qualified nodes. Then for each node, I have to see which is the nearest. So I have to find out the distance. And whichever is the nearest, that should be taken as the most suitable node. And it forms a triangle with that. And after the triangle is formed, the E is to be updated. Whatever edges are already there in the E in the triangle, they are to be removed. And the new edges that are formed are to be added in the E. And if there is any interior node is made into a triangle, that interior node is to be removed from the I array. And again, now in the present E array, whichever is the last one, that becomes the next advancing friend. And again, this procedure is to be continued. So there may be a chance that a new triangle which is formed, all the three edges may be in the E, then all the three edges are to be removed. And I have to get what is the new friend. So I have to number them again and find out what is the last edge, and that becomes the new friend. Like this becomes the new friend. So when this triangle is formed, all these three are to be removed, and this is to be made the new friend. Like that. Okay, this is the way I have to continue the procedure till all the edges in E are removed and all the nodes in I are removed. Okay, so that is the way. Any questions? Okay, similar procedure is to be done for doubly connected domain. Okay, only small initial thing only will be different. And what is the difference? Okay, this is the type of doubly connected domain if I have. Okay, this is that. And only numbering initially I have to. The domain consists of one object within the domain. And the advancing friend array E is composed of both the outer boundary and inner boundary. Now I have edges on the outer boundary and also in the inner boundary. And the arrangement of the outer edge E0 must be in counterclockwise order. And the edges EI on the inner boundary should be listed in the clockwise order. Okay, this is the one thing you have to keep in mind as shown in the figure. And numbering of nodes is random. Okay, nodes can be random, but edges should be in the counterclockwise and clockwise. So on the inner boundary, I have 1, 2, 3, up to 6. You can see here. So this is one, okay, I think this. So 1, 15, 16, 2, 16, 17, 3, 4, 5, 6. These 6 are named here. And then from 7 onwards, so this is 7, 8, this is in the counterclockwise. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 edges are there. Okay, so 16, 6, 1 will be the last edge, which will become the advancing friend. Okay, so 1 to 6 and 7 to 16, 16, 6, 1 is the advancing friend. And interior nodes 8, 9, 13, 14. There are 4 nodes 8, 9, 13, 14. These are the 4 nodes in the interior. That is in the I array. And the advancing friend algorithm is same as applied to simply connected domain. A total of 24 triangles are generated. The dead end situation comes after triangle 21. The triangle proceeds from edge 17, 18 towards left. Okay, so we can see that actually total 24, and it is given in the order, which is the first triangle formed, the second triangle, third triangle, fourth triangle, like that. You can see, you can try by hand how it comes triangle after triangle like that. So you can check it. This is a doubly connected domain. Similarly, we can have multiply connected domain also. So multiply connected domain means there can be more than one object within the domain. So a domain is shown in the next slide with 2 objects within the domain. Yes.
Sir, in the here,
Yeah.
the vertices number,
Yeah.
how it gives?
Vertices numbers, I told it can be in any order. It can be random. Numbering of nodes is random, but edges must be in sequence. Is it clear? You can number them in any way, but each edge should be given the nodes in the brackets, whatever edges, nodes it consists of. It can be numbered in any random manner.
Sir,
It
how
doesn't
we
matter.
get the last edges?
How means? So here you start at some point here. Maybe you should be in the clockwise. So it is started with 1 here. 1, 2, 3, 4, 5, 6. Okay. And it started from here. It need not be here. It can be started here. No problem. Okay. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 edges are there. So whatever is the last edge, okay, that will become the advancing front. From here, I have to start. What is the nearest node on the left side? I have to find out. So it is found out like that, and it is drawn this way. Okay,
So the last node can be anywhere, sir?
last node
Can be anywhere except
can be
this
anywhere.
edge?
It can be anywhere,
Okay, sir.
right? I have to find out what is the last edge in my numbering, and with that last edge, I have to start doing it. So it is always convenient if your last edge comes here this side, so that I can proceed in a comfortable way. That's all. Okay, so like that I have to do. And doubly multiply connected, yes.
Sir, last edge also will be anywhere.
Last edge,
Also will be anywhere.
yeah, it can be anywhere. It can come here sometime. It can come here, no problem. So this will become the first triangle, and I have to go in sequence. Okay, like that. So multiply connected domain, it is example taken. This is one object here, and there is another object here. Okay, so like that. And again, the numbering and all things will be in the same way. Okay, a domain is shown with next slide with 2 objects within the domain. The domain is normalized where a total of 35 interior nodes have been generated. Okay, in domain normalization, we got them. Okay, total 35 internal nodes, interior nodes are there. Then the advancing front method is used to triangulate the domain. A number of 116 triangles are formed. For the purpose of clarity, the order of formation of the triangle is shown in the figure. Okay, what is the first and what is the next one? Like that, it is given here, like this, here. Okay, if this is the one, actually he has not given 2 here. Okay, you can write them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like that. So the order of triangles that are formed is given here. You can check, right? So you can try yourself and see how it is going. You can try manually how it comes. Okay, so next class we will discuss about Delaunay triangulation. Any questions? So you go through the problems and you try to draw manually and see how you are getting the triangles. Then you can understand what is the dead end and how you have to proceed from there. You can understand, right? Okay, if there are no questions, we will go for the story. It's a nice story. Disciplehood story. When the great Sufi, it is a Sufi story. When the great Sufi mystic Hassan was dying, somebody asked, Hassan, who was your master? He said, I had thousands of masters. If I just relayed their names, it will take months, years, and it is too late. But 3 masters I will certainly tell you about. One was a thief. Once I got lost in the desert, and when I reached a village, it was very late. Everything was closed. But at last, I found one man who was trying to make a hole in the wall of a house. I asked him where I could stay, and he said, at this time of night it will be difficult, but you can stay with me if you can stay with a thief. And the man was so beautiful. I stayed for 1 month with him. And each night he would say to me, now I am going to my work, you rest and you pray. When he came back, I would ask, could you get anything? He would say, not tonight, but tomorrow I will try again. God willing, tomorrow it is going to happen. He was never in a state of hopelessness. He was always happy. When I was meditating for years on end and nothing was happening, many times the moment came when I was so desperate, so hopeless, that I thought to stop all this nonsense. And suddenly I would remember the thief who would say every night, God willing, tomorrow it's going to happen. Okay, that gives me hope. That is the hope one should have. And my second master was a dog. I was going to the river thirsty and a dog came. He was also thirsty. He looked into the river. He saw another dog there, his own image, and became afraid. He would bark and run away. But his thirst was so much that he would come back. And many times it went and came back like that. Finally, despite his fear, he just jumped into the water and the image disappeared. And I knew that a message had come to me from God. One has to jump in spite of all the fears. And the third master was a small child. I entered a town and a child was carrying a lit candle. He was going to mosque to put the candle there. Just joking, I asked the boy, have you lit the candle yourself? He said, yes, sir. And I asked, there was a moment when the candle was unlit. And then there was a moment when the candle was lit. Can you show me the source from which the light came? And the boy laughed, blew out the candle and said, now you have seen the light going. Where has it gone? Will you tell me? My ego was shattered. My whole knowledge was shattered. And that moment I felt my own stupidity. Since then, I dropped all my knowledge ability. It is true that I had no master. That does not mean that I was not a disciple. I accepted the whole existence as my master. My disciplehood was a greater involvement than yours is. I trusted the clouds, the trees, and I trusted existence as such. I had no master because I had millions of masters. I learned from every possible source. To be a disciple is a must on the path. What does it mean to be a disciple? It means to be able to learn, to be available to learn, and to be vulnerable to existence. With a master, you start learning to learn. The master is a swimming pool where you can learn how to swim. Once you have learned, all the oceans are yours. Thank you. Thank you very much.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Sir.